Evening, everyone. Tonight we're going to go back to chapter 9 and start talking about differential equations. Okay, so let me share the screen here. The Lakers are just getting pummeled. All right, so here's where we left off yesterday. Okay, so text mode here. 185 and the equations. Okay. The draw mode. And do this. Okay, so we're gonna have to start with a bunch of definitions and results. Might not be able to prove all of them for us today. Matter of fact, a bunch of them we're just going to leave. Okay, so we are back into chapter 9. Okay, so let's see here. For an example here, let's suppose that we have a spring and we have a mass attached to this spring. Okay. Okay, so there are two forces acting on this mass. One force is acting this direction, and that would be the force due to the spring. Force due to the spring. Okay. And there's also this, that looks too much like a G. Force due to the spring. And then we have force due to gravity. Okay. And with gravity, force is going to be going down. Okay, so let's say that this is at equilibrium right here. Okay, like that. And we've got some kind of a axis here. Maybe we'll call it the x-axis. And if we come and grab the mass and just pull it down or push it up and let it go, the thing is going to wiggle back and forth. Okay. Now the goal is ultimately to figure out what the equations of motion are. Okay. All right. So what we learned, we don't need that much. long time ago, the time of Newton, one of his contemporaries named Hooke decided that the force that comes from the spring is going to be negative Kx, where, let's say, K is a positive and X equals the displacement. Okay. So sometimes if we want to designate something to be positive, we sometimes might write it as, you're going to see this a lot, omega squared x. Or there, it's no doubt that omega squared is a positive number. Okay, but we'll just stick with the K. Okay, so then we have Newton. Okay, now Newton says that the force due to gravity is the mass times the acceleration. But this isn't exactly what Newton said. What Newton said in the Principia is that the force is the instantaneous rate of change of momentum. That's what he actually has in the Principia. And the letter that we usually use for momentum for you guys, since this is 185, maybe you guys have started your physics courses. Any of you taking a summer physics course?
Yeah.
Yeah, okay, so I think P is the letter that we use, for momentum. Okay, well, as you do this, you write down, well, it's the momentum is m times v. Okay, now the mass is constant, and so we're going to have m times the derivative with respect to t of velocity, and velocity is dx dt, right? From back in our Calc 1 days. And so what we're going to get is that the force due to gravity for Newton is going to be m times d squared x dt squared. That's what we get. Okay, now at equilibrium, these forces have to cancel each other out. Okay, so this is where now the sign that you put in front of things starts to make a difference. So if we were to, at equilibrium, these forces have to cancel each other out. Force due to this has to be the force due to that. Okay. Now you can like go nuts with, okay, what's going to be positive and what's going to be negative. If you set these two equal to each other, we're going to get that this mass times d squared x dt squared has to equal negative kx. And if I reorganize this, divide through by some stuff, we're going to get d squared x dt squared plus k over mx equals 0. Since k over m is positive, call it omega squared. And so what we arrive at is this equation. Okay. Now the goal here, this is what we call a differential equation. And most of the time I just write DE for differential equation. Okay, so obviously here, the goal is to solve for x of t. That's what the goal is. Let me shut this door. Okay, so the definitions are now going to start. So this is why Newton organized all of the calculus results, is because he needed calculus to solve these kinds of equations that he was coming up with. Okay, in his year that he spent away, and he left school and he went and hid out in the countryside during the Black Plague. When he came back, he had all this. So who knows what really happened? Maybe aliens gave him all the information. Okay, so definition. A differential equation is an equation in an unknown function and its derivatives. Okay, so example, look above. Okay, so the study of differential equations, what you'll find is that these things just get classified as this type, this type, this type, this type. And if this happens, do this. If this happens, do that. Okay, so we need to kind of make some sense out of this. So another definition for us. The order of a differential equation is the largest derivative in it. Okay. So the above example, that's a second order differential equation. All right. Now, for reasons that will become a little bit more clear when you get into Math 285, and I could even do it here in Math 185, we focus on solving first and second order only. The reason for this is because eventually we're going to be solving systems of differential equations. And if you have a third order differential equation, it's possible to turn that into a system of second order differential equations. Okay, and the same with fourth order and so on. All right. And so all the machinery that and software that gets written is all based on, okay, you've already put the problem into the form that it needs to be in to go. Okay. Okay, so now we need more of a definition here. So a function, let's say x of t, is said to be the general solution of an nth order differential equation if, number one, it is a solution. Two, it contains n arbitrary constants and number 3, any solution can be obtained from it by assigning values to the constant. Okay, so Shoei grade 1 to 2 strain, can throw in 4 to 6 weeks. Now let's hope he doesn't throw anymore. Period. Sucks. Okay, so this might seem like an unusual definition. You know, why would you define the general solution? You know, like, wouldn't you just go try to find it? Okay, well, what happens in mathematics, the further up, the higher up you go, quite often, really good theorems become definitions. I remember asking this same exact question there was a married couple at Cal Poly Pomona in the math department, Professors McKinney. And then they got divorced, and it was kind of uncomfortable. I worked for the math department, so, you know, I was always around. Anyway, I asked her one day about this. I go, I don't get this, you know, and she's like, okay, good. This lets me know you're actually thinking about some stuff here. And this is when she, you know, said that to me. Okay, so now there's a fact that I want you to realize here. Not every differential equation has a general solution. Okay, now it's in my 285 notes, which I've got packed away in this thing over there. So I'll take a stab at trying to guess it. Y prime plus y minus 1 equals 0. No, that's not it. I don't know. I'll try to dig it up and find it, but it's not that important for us to know the specific example of what it is. Okay, so now you might be wondering, okay, well, why n arbitrary constants? Well, if I gave you this problem, and there are problems like this back in the Math 180 section, where I said, okay, if we said x 5 derivatives is equal to whatever, like let's say 0, then we would integrate and say that the 4th derivative of x would then be any arbitrary constant. The 3rd derivative would be the arbitrary constant x plus another arbitrary constant, and then integrate again, and we would have this c1x squared plus c0x plus, I should have done this as c2 plus c3. And one of you is no doubt saying, oh, he messed up. It's x squared over 2. Nope, I just absorbed it in the constant. So now x prime is going to be some c1x cubed plus some c2x squared, c3x, c4. And then the last one, of course, will have all 5 arbitrary constants. Okay. All right, now you've been solving differential equations this entire time ever since chapter 5. You know, I could have a differential equation like this, dy dx equals x times the natural log of x.
I think you muted yourself. Still can't hear you. No, still can't hear you. Oh. Did we lose him then?
Probably.
Ah, crap. It still shows that he's in.
Yeah, I think it takes a while to show up in either of our screens.
Um,
Hey, Eduardo.
yeah.
Um, uh, are you able to solve questions on your own after the class?
Sometimes I am. I mean, some of these are a little bit difficult.
Like, aren't they pretty confusing?
They're pretty confusing.
Yeah.
I will. I'm watching. I like after this class. Sometimes like I'll go back, look
Mm-hmm.
at the what section that he's doing, and I watched YouTube videos on how to solve some of the problems in the book.
So like when you solved the previous chapter, so it was 11, right?
Uh-huh.
In 11, is it mostly like just formula usage, or is it like however he derives it? Like, do you go deep into the derivation and then take parts out of that, or is it just plug in the formula and then get the answer?
So for some of them, you have to derive them first, and then plug them into the formula to get
Oh,
your answer. And then for
okay.
some of them, for the lot higher like numbered questions, you have
Mm-hmm.
to first derive them and then plug them in. Like you have to do it backwards.
Oh.
Yeah.
Oh, okay. That's weird.
There was a video of, I can't remember the guy's name. I didn't even save it either. Of a guy that literally, instead of even just solving them, he'll look at it and then he'll
Yeah.
grab the first two numbers in the sequence, and then
Uh-huh.
the first number in the sequence, and then the last number of the sequence,
Uh-huh.
and then he would use the formula to solve it without even
Oh,
without even getting the rest of the.
yeah.
Yeah.
That's nice.
What are you crazy guys talking about, huh? What's this stuff?
The last chapter.
Last
Yeah.
chapter. I like that word last. Are we done with this class almost?
Oh, I wish.
No.
I wish.
We're ending a week early. Hooray!
Oh no, I'm like a chapter behind.
Oh, me too. Trust me.
I've been playing catch up after like the last section that we did.
Yeah.
What are you talking about, man? This stuff's so easy. It's just theoretical, hypothetical math with no numbers. How do you not see how easy this is?
Oh
Here.
my God.
All right,
Finally,
how
you're
long-
joining us, Bobby.
How long was I out?
I don't know. I just got here.
Like 5
For like
minutes.
5 minutes, yeah.
Just 5 minutes?
Yeah.
This time it happened real quick. Okay, let's get back to where we were. Share the screen. Okay. So what I was pointing out here is that you guys have been solving differential equations since you've been integrating. Okay. And I pointed out this e to the negative x squared thing where, yeah, it doesn't have an elementary antiderivative, but there is something you can do. You know, you can use the Maclaurin series and integrate that, and that's what we did. Okay. Now, the reason I use that as an example was because of this theorem. Okay, so I have a function of two variables continuous on a rectangle. Okay, so what that means is a lot different than what it means in the two variable case, than the one variable case. If you're continuous, it means the limit has to be the same coming in any different direction. Okay, so for you guys that are going into 280, that's what you're going to be learning in the fall. All right. So, and then we're supposing that the partial derivative of f with respect to y is continuous on this open set, which is the interior of R. Okay, now this notation, this is partial derivative. Okay, so what it is, it doesn't matter how many variables you have. It's called the partial derivative of f with respect to, somebody's got their music playing, with respect to y. Okay, so you just pretend that you just pretend that all the other variables are constants, and you come on. We gotta go to participants. Somebody's got their mic going. You can hear them. There we go. Okay. Share the screen. Start. Okay, there we go. Here's OneNote again. Okay. So you just hold all the letters constant and you just take the derivative. Okay. The conclusion is then the first order I get more set up to write down. Okay. I'll just write down the conclusion. Then the first order differential equation dy dx equals f of xy has a unique wait. Erase this. Along with the condition that y of x0 equals y0 has a unique solution. So basically what this is saying is that any differential equation you can write down has an answer, as long as it meets these criteria, okay? So a differential equation together with some conditions is called an initial value problem. Okay, now the proof of this is too hard for us. Barely. I don't know if this is how you spell barely, but.
It is.
So what happens is he takes the differential equation and he converts the problem into finding the limit of a sequence of functions. Now, we just got done talking about sequences of numbers. So where the math majors are going to be going, and some of the physics majors, and a few of you electrical engineering people, you're going to be looking at, okay, now we've done sequences of numbers, now let's do sequences and series of functions. And these things are called Picard iterates. And I could actually, over a 2-day period, I think, walk us through that proof. There's not a whole lot out of your grasp. And it's in the appendix, at least it used to be, of my Math 285 book. So anyways, okay, so definition. And nth order differential equation together with n initial conditions is called an initial value problem. An initial value problem. IVP. So another way of saying this above is that then the IVP given by dy dx equals f of xy together with the condition y of x0 equals some y0 has a unique solution. Okay, now sometimes the unique solution is not very satisfying, like case in point up here with this e to the negative x squared thing. But all of us trying to illustrate is that this theorem works. Okay, so that's the existence and uniqueness theorem with the differential equations. And let me move this stuff over here. Now, chapter 9, I'm just going to pluck out the differential equations. I'm not going to cover all of chapter 9. Okay, so section 9.1 it's kind of like an introduction. He gives you some stories, like he retells the story that I'm telling here with the spring. Okay. And then he does some definitions. Now, in the first section, about all that he's asking you to do is verify certain things, like verify that this is a solution to the differential equation. So if you need practice taking derivatives and so on, you can do that. Okay. 9.1 is the intro. 9.2, this is where we have all of the geometric results. Now, I'm going to leave it for your 285 professors to talk about the slope fields and the isoplines and stuff. Okay. But you might just want to read through that section. Well,
Can you list them on this so that way I can just copy that down so I can look those up?
well, I mean, it's all right here in section 9.2.
Oh, okay.
So, like, for example, he talks about Euler's method. For year, this is a method in solving a differential equation. Years ago, I used to get mailed the high school AP exams, the math ones, just to give us, well, we all were, just to give a heads up. Here's what they did. And then remember, these 10 free response questions, 5 of them were, what does Euler's method say here? What does Euler's method do you solve? Well, using Euler's method. It's really not that important, okay? But it's something you can kind of read through. Okay, so 9.3, this is where we start talking about specific guys. So 9.3 is going to be first order. Everything in chapter 9 is first order. First order separable. Differential equations. First order separable differential equations. Okay. So the idea is this. Definition. A differential equation is said to be separable if it is of the form dy dx equals f of x over g of y. Okay, now the reason for the word separable is because if this is the case, you think of dy dx as a fraction. And so when you cross multiply the things, you would get g of y dy equals f of x dx. And so the question is obviously, okay, can I just then integrate both sides and be done with it? So let's see. Can we integrate both sides? This is a question I don't think we've asked yet in our adventures in calculus. We've talked about taking the derivative of both sides, you know, when we were doing the implicit differentiation. Okay, so we should probably at least make an attempt to justify this here. Okay, so let's see. If I want to integrate y, if I want to integrate g of y dy, I'm going to do a variable substitution where implicitly we think that y is a function of x, right? And so if I was to do a trig substitution style substitution, g of y of x, and then like, let's say I was going to say y is the sine of x, then we would have to say dy is cosine x, so we would have to write dy dx, that's the cosine x thing, then times the dx piece. Okay, now the dy dx piece that was given to us above as f of x over g of y dx, and then these things cancel, and what you end up with is the integral of f of x dx. Now, some of you maybe were waiting for a little bit more juicy of a proof or more penetrating or something like that. I don't know. It's kind of a letdown. But basically, you just are going to integrate both sides. Okay? So these separable differential equations, these are the ones where you quite often get implicit solutions. So like, for example, dy dx equals x times y. Can I separate this? Sure. I can go dy over y equals x dx. Okay. Okay, now we start playing games with the arbitrary constants. So this kind of stuff, sometimes you solve something and you look in the back of the book and doesn't look like what you have, and your friend has a different answer. But depending on how you're doing your implicit stuff, this one shouldn't be too terribly bad. Okay, so we're going to integrate both sides here. Integral dy over y equals the integral of x dx. Okay, so now this would be the natural log of the absolute value of y is going to be x squared, plus some constant c1 is equal to x squared over 2 plus some constant c2. So I'll lump those arbitrary constants together to get the natural log of the absolute value of y equals x squared over 2 plus some arbitrary constant c3. Now I'm going to go e to both sides. And when I do that, I would have the absolute value of y would be e to the x squared over 2 plus c3, which is e to the x squared over 2 times e to the c3. And I'll call e to the c3 c4. Okay, now, this constant isn't so arbitrary anymore because it must always be positive. Okay. But look, it's the absolute value of y over here. So that's kind of good news. All right. So now the next straw is to say, okay, then y is going to be either C4 e to the x squared over 2. I don't know why I put 4 there. X squared over 2 if the y is supposed to be positive, or negative C4 e to the x squared over 2 if the y is supposed to be negative. So what we do here is, why don't we let C be the following. C4 if y is positive, negative C4 if y is negative. And so our final answer here is y is going to be C e to the x squared over 2. Okay. Okay, so these are some things you might want to practice before you step into the 285 class. Okay, I'm also going to go a little bit further and give us another first order guy. Okay, so let's do this example. Okay, so what we want to do is solve the initial value problem. X times y prime plus y equals y squared. And y of 1 has to equal negative 1. Okay, so this is going to be separable because we haven't looked at anything else yet. So I've got x times dy dx is equal to y squared minus y. Okay, now the next thing I'm going to do is the obvious. I'm going to say this is going to lead to dy over y squared minus y is equal to dx over x. Okay, now at this stage of the game, there are some restrictions. The y cannot be 0, nor can y equal 1. Okay. But up here, those restrictions weren't there, up in the original differential equation. Okay, so generally with these things, you have to keep track of this stuff. Okay. All right, so obviously we're going to integrate both sides. So I need to figure out the partial fraction decomposition of y times y minus 1. And that's the natural log of the absolute value of x, constant c. Okay. Let's see. Let me do that real fast. That would be the partial fraction. 1 over y, 1 minus 1, a over y, b over y minus 1. So 1 equals a minus b, y is 0, a is negative 1. And then when y is 1, the b is 1. Okay, so it's the integral of 1 over y minus 1 minus the 1 over y dy. This equals the natural log of the absolute value of x. Let's see. And I'll integrate this stuff. So this is going to end up going to be the natural log of y minus 1 over y plus a constant c1 call that the constant C2. Okay, so this is telling us that this is the natural log of absolute value of x. Okay, so now I go e to both sides, and it's going to be e to the this is e to the that. So that means we're going to have the absolute value of y minus 1 over y times another constant, C3, is going to be the absolute value of x times another constant, C4. Because the reason for this is e to the log of x times e to the C2. Okay? So now I'll divide the constants up, and I'll say, all right, y minus 1 over y is going to equal some constant C5 x. Okay, so if the absolute value of two things are equal to each other, that means that the y minus 1 over y is going to be plus or minus some constant c times the x. Okay, now when are we going to use our condition? Well, the condition was that y of 1 is negative 1. So when x equals 1, y equals negative 1. Okay, so negative 1 minus 1 over negative 1 has to be plus or minus the c thing. Well, that tells me that the plus or minus c thing is going to have to equal 2. So the question here is, does the plus and minus stay in the problem or not? This is the reason why I selected this problem. These are the kinds of things that you start to have to think about. Okay, so y minus 1 over y, what we got is going to be plus or minus 2x. So if I was to go y minus 1 equals plus or minus 2xy, I'm going to try to solve this for y. So y minus or plus 2xy equals 1. So y times 1 plus or minus 2x equals 1. So y equals 1 over 1 plus or minus 2x. Okay, now I want to check both of these answers. So let's let y1 be 1 over 1 plus 2x, and let's let y2 be the other one. Before we get too far down the rabbit hole with these differential equations, I want you to really get a feel for this. Is kind of important. Like, you know, some of you are gonna, on the test, the answer might be y squared minus x squared equals 1. So y equals x, y squared equals x squared plus 1. Then you'll neglect to put the plus or minus in front. And in differential equations, that's important because that's a whole nother batch of solutions that you're missing. Okay, so we're going to check both these things. The original differential equation was x y prime plus y equals y squared. Okay, so let's do the derivative here. the derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. Okay. And so if I was to take x times y prime, that's y1 prime, x y1 prime is going to be negative 2x over 1 plus 2x squared. And I'm going to now add y to it. So x y prime plus y. So I'm going to have 1 over 1 plus 2x minus 2x over 1 plus 2x squared. If I common denominator this, it's going to be 1 plus 2x minus 2x over 1 plus 2x squared. That's 1 over 1 plus 2x squared. And don't you love it when a plan comes together? That is y squared, right? Y1 squared. Okay. Okay, so we know y1 worked. Okay, let's check y2. So for y2 prime is equal to derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. Okay. And so x y prime plus y is going to equal 2x over 1 minus 2x quantity squared plus 1 over 1 minus 2x squared. 1 minus 2x. Common denominator it up. And that's going to be a 2x plus 1 minus 2x over 1 minus 2x squared. And once again, and that is y2 squared. Okay, so moral to the story. Don't ignore the pluses and the minuses. Generally, we try to lose them at all, whenever we can. Like, for example, like let's say we had a problem like this. Dy dx equals x, oops, trying to make one up here on the spot that does this feature I want it to do. It's going to be y over 2x. Okay, so this is separable. Now, one way of proceeding would be to do this, would be to say that dy over y is equal to 2x dx. I meant to put this, switch this from 2xy. Okay, so that's one thing. And No, that's not what I wanted either. Start over. Took all my differential equation notes and I put them in the 285 folder. X, Y over 2. That's what I want. Okay, so one separation technique would be to do it like this, and then this would be X over 2 dx. Another technique would be to say that 2 dy over y is equal to x dx. Okay, now the reason, anytime there's more than one way to do the problem, I strongly encourage you guys to do more than one way. That's how I learned a lot of stuff. Got baseball on right now, just the rest of the night, just put the game on after we're done, just do problems. Okay, so this, by using number 2, we're going to get 2 natural log of absolute value of y is going to be x squared over 2, and then I'll put just the constant out there. Okay, now the reason I did this was because I can move that to the inside and get rid of the absolute value signs. Now sometimes with this 2 here, calculus doesn't play well with absolute value signs. So anytime you can get rid of them, it's a good idea. So for this problem, we would have y squared equals some constant e to the x squared over 2. Okay, so in the 9.3 exercises, and he doesn't really have a lot of them, you know, it's good practice in integrating, and you know, I would, you know, do in my book just the reasonable problems, you know, the ones that are just don't have a story attached to them. Okay. The next thing we want to talk about, I'm going to skip 9.4, let you read it yourself. This is exponential growth and decay. All I'll say a little bit about this is that it's just a separable differential equation. So if you have this model, you hear about scientists are looking for models, the model of the universe. Stephen Hawking, his whole life, trying to fix the gravity issue with in quantum mechanics. They're looking for models. Einstein is famous for E equals mc squared, right? Because that looks good on a t-shirt and everyone can understand it, and you know, even my brother. Okay. But if you look at what Einstein really came up with was a set of differential equations that are very, very hardcore. And that's what they're trying to look at, trying to find. Even on his deathbed, he realized he made a mistake. I had an original thought one night. There's this idea that the speed of light can't be exceeded. But what if it could? What if the speed of light is just the amount of time it takes to go from one end of the universe to the other, and that amount of time never changes, like entangled particles? Anyways, I get carried away there. Okay, so anytime you have a model that looks like where the rate at which your quantity is changing is proportional to how much you have in the first place, this is a growth model. If K is positive, and a decay model if the K is negative. Okay, now this is just a separable differential equation that you go through and solve. Okay, and so I'll leave it for you to go read what you want in that section, but if you want to do some of those physics problems and biology problems and stuff, you know, go ahead. But I just want to stick to the basic. Okay, so I'm going to go ahead and skip 9.5 altogether. Okay, and this is more Newton's law of cooling, direction fields, and it's, no one ever remembers any of this stuff. If it ever shows up, you know, you have to do a review. Okay, but we are at a place now where we have another technique. So 9.5, linear first order differential equations. Okay, so start with an example. This is a pretty harmless looking example. All right, and no matter how you try, you're not going to be able to separate this thing. Yet it should be kind of, looks like it should be doable, right? Okay, well, try as you might, you're not going to be able to do that. Okay, so here's the general definition. An nth order linear differential equation is of the form. I think I just remembered the example. The example of the one that doesn't have a general solution is not linear.
Bobby,
Yep.
are you doing 9.6 or 9.5?
Oh, we're in 9.6.
Oh, thank you.
Brain fart. Okay, so it's going to be of the form a sub n of x y nth derivative plus a sub n minus 1 of x y n minus 1 derivatives dot 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 plus a1 y prime plus a0 y equals some function of x. Linear means you are linear in the y stuff. Okay, it doesn't matter how jacked up these functions of x are. That's a1 of x, that's a0 of x. I just kind of got lazy. Okay, so the best way to illustrate linear is by one that's not. So not linear would be something like y prime squared plus y prime equals x or something like that. Okay, you don't have the y stuff being multiplied with each other and none of that. Okay, so this example above is going to be linear. Okay, so a general first order linear let's see, it would be a of x times dy dx plus b of x times y plus, let's say, equals c of x. We generally put that thing that doesn't hit the y on the right side. So by the way, if the f of x is identically 0, we call that homogeneous. Okay, so this is what it would look like. All right, now there's a standard form that we're going to put the problem in. Because a long time ago, and it was probably one of the Bernoulli clan, figured out that if you put it in this form, you can figure out a solution. Okay, so if once the differential equation gets reported to you, that is what the law of the land is. Okay. Now, in order for us to get from the first one I wrote down to the second one I've got written down here, I had to do some dividing, right? Like I'm dividing by a of x. So there is no restriction of a of x equaling 0 in the original thing. So you have to keep track of that stuff. Okay, now, what if, this is how the solution goes. What if we could find some function I of x that has this amazing property that if we take I of x and we multiply it by dy dx plus p of x times y, it would collapse into the derivative with respect to x of I of x times this y. Okay, now, if we could do such a thing, we would multiply both sides of the differential equation, and I'll drop the of x now. We would multiply both sides of the equation by this I thing. By design, that's going to collapse into the derivative of I times y prime. Okay, and so then that would mean that IY would be the antiderivative of this IQ, and there'd be a plus C out there. Divide both sides by the I get 1 over I integral IQ plus the arbitrary constant over the I. Okay. Okay, now that's wishful thinking maybe. Okay. Well, let's see if we can figure this out. Now, we got a lot to keep track of. We're multiplying both sides of an equation by I of x. And then we just went yard. 1-0. Stasi. Max Stasi. Okay, so let's look at this condition on I. All right. So what we need here, let's write down what's needed. What we need is to have the derivative of I times y equal to I times y prime plus I p y. That's me just distributing all that stuff right there. Okay, so I use the product rule. I prime y plus I y prime. That must equal I y prime plus I p y. These two things are going to cancel to get I prime y equals I p y. Okay, so now what we're going to do is we're going to remove the y. The condition that we're interested in would lead to I prime equaling I p. Okay, now there's a lot of words that go in with differential equations, and the kind of thing that you would say now is, well, certainly if I satisfied this property, then it would satisfy the property above it, right? Well, this is a first order separable differential equation. di dx is equal to I times P. So what we can do here is we can separate it and get that di over I is equal to P dx. Okay, now we're not looking for the most general I, we're just looking for any I that does the trick. Okay, so after integrating this, we would have the natural log of the absolute value of I would be the integral of P dx, and I'll say plus C, but set to 0. All right. We would absolutely e to both sides, and this would then be the integral e to the integral of P dx. Okay, so I would be plus or minus. So what we're going to do is we're going to select I to be this e to the integral of the P dx. This is what we call the integrating factor. Okay. All right, so before we get in and do the specific problems with this stuff, notice that since I is e to something, it's never 0. So that question was asked and answered now. Okay, so if we do that first one I did, all right, you said, all right, let's look at this guy. Dy dx equals x plus y. We have to put it in a standard form. So dy dx minus y is equal to x. Now you identify the p. You integrate the p. The integrating factor is going to be e to that thing. Okay, so if you were to take e to the negative x and multiply both sides x e to the negative x, then by design, this should collapse into y e to the negative x prime. Okay, now just verify that that worked. The answer is going to be, the derivative of that is going to be negative y e to the negative x plus the y prime. So it's all right there. So that means that y e to the negative x is equal to the integral. And so now we're back to having to know how to integrate. U is x, du is dx, dv e to the negative x, v negative e negative x. So this is going to be uv minus the integral of v du. So that's going to be negative e to the negative x, e to the negative x minus e to the negative x plus a constant c. And so the y then is going to be negative x minus 1 plus c e to the x. Now, if you didn't have the plus c, you're going to miss that entire part of that solution. One might think, oh, this is modeling something linear if this part of the answer wasn't there. Yet your model isn't matching up with your experimental results. If they turn that, that's it. I thought that was live. Okay. Okay, so for these separable guys, I mean, these first order linear guys, you might want to get in here and, you know, do some of these. He doesn't really have a lot. If you guys are having to go to Math 285, it would not be a waste of your time to find another resource like OpenStax and just do a bunch. Okay. Who are the 285 teachers? Art, but I'm sure he has the honors. I think Stan, Tyler, maybe Andy. Andy is very differential equation heavy. So is Jack Hoffman. Okay, so let's see. So this next example is not exactly first order linear. This is called a Bernoulli differential equation. Where it's almost first order linear. Okay, so the standard form for this thing would look like this. And then it's q of x times y to some power, n. Okay, now n could be any real number that we want. Okay, so there's some things here to consider. If n equals 1, that's a separable differential equation. And bringing the p of x over or factor the y out. Okay. If n equals 0, that's just first order linear differential equation. Okay, so the trick here, generally what we do is we're going to divide through by y to the n. So this would give me y to the negative n times dy dx plus p of x times y to the 1 minus n equals q. Oh, now the thing to recognize here is that, and this is what Bernoulli saw, and he didn't just write this down and say, I named this Bernoulli, okay? He solved a differential equation using this technique, and people started saying, using Bernoulli's technique, Bernoulli eventually becomes a Bernoulli differential equation. So if I was to let u be this y to the 1 minus n, then the derivative here is going to be 1 minus n y to the negative nth power, then dy dx. And I want you to see that that piece is right there. Okay. So if we make this substitution, I'm going to have 1 over 1 minus n times du dx plus p of x times this u equals the q of x. So if I multiply through by 1 minus n, now remember, we wouldn't be doing this if n is equal to 1 because it would be separable. Du dx plus 1 minus n p of x times u equals 1 minus n times the q of x. Okay, so here, this is first order linear. The new p is 1 minus n p of x. Okay, So he only has 3 exercises in there, so you might want to, do that. Okay, now the next topic is not in the book. So you might need to take careful notes. Exact differential equations. Okay. Now, the reason I'm going above and beyond the class here is because in 280 and in 285, which for most, I have to have some kind of a goal here. My goal in pre-calculus is to get you ready for calculus. That's it. I don't care about anything else. The goal in this class is to get you ready for the next 2. Okay. So I think it would be worth your time to look at this. Okay. Okay. So definition. An expression of the form m of xy dx plus n of xy dy equaling 0 is called a differential one form. Okay. Okay, now an expression of the form, I don't need equal to 0. Okay, everybody erase that. Okay, now a 2 form, this is just for Eduardo and the physics major. A 2 form would be something which is we call a wedge product. Okay, and the way that wedge products operate is they are anti-commutative. And when I first joined Orange Coast College as a full-time faculty member, the big hot debate in the department was, should we be showing the Math 290H people wedge products? That's what these are. And Art said yes, and I thought, why the hell not? If any of you are planning on taking 290H, you're going to need to do it quickly before Art leaves. And I'm either Stan or Tyler, I think, might inherit it, but it's probably going to change. Once the bookstore opens up, another thing, I did this for this kid that graduated with my oldest boy, but he graduated from Harvard. He came home last summer and took 285, and it was supposed to be Art. He said it with me. And so I went over to the bookstore and I got every single handout Art ever has done. I dug around in my notes. I got all of his stuff that I rewrote, and I made copies, and I just handed it all to Christian. So Art has a way of explaining really complicated things with very easy examples. And he does this wedge product stuff here with determinants. And he shows that, well, if you switch 2 rows in a matrix, the determinant changes by -1. Okay, now we get a differential equation if we set this equal to 0. And this is why. If I set m, I'll drop the of x and y stuff, then what we can find here is that dy dx is going to be negative m over n. Okay, so we do get a differential equation. Okay, well, In Math 285, you'll be looking at it from this point of view. In Math 280, it's always a P and a Q. Okay. Okay, so for both Math 280 and 285, we have to discuss something. Okay, so let's let F be a function of two variables, X and Y. Okay. The differential of F is defined as df. And what it is, it's the partial derivative of x with respect of f with respect to x times dx plus the partial derivative of f with respect to y times dy. Okay, now compare this where if I had f was f of x, then df would be just f prime of x dx, or df dx equals that. So this is kind of how this generalizes. Okay, now here's the story. What if m of x y dx plus n of x y, what if how do you explain to a non-native speaker why you put an H after the W in the word what? Other than English is stupid. So what if this equals df for some f? In the 285 class, the book I use, we have this Greek letter being used. Okay. Well, then if that was the case, and you had the differential equation m dx plus n dy equals 0, that would mean the differential of f is equal to 0. Now think of the differential as the derivative type thing. Well, wouldn't that tell you that the f has now got to be a constant? Okay. All right, so there's some things here like, okay, so what are you saying? What's going to be the answer? Well, if we have this f of xy equaling c, then we know that partial f partial x dx partial f partial y dy is equal to 0. Which is meaning that the m dx plus the n dy is equal to 0.
Hey, Bobby,
So then,
are those twos or is that a weird symbol? Because I've been writing those as weird symbols for a while.
yeah, they are not twos.
Okay.
you came in a little late, I think. So this is it's sort of like it's supposed to look like a scripted D. So this is read partial F partial Y. So let's give you an example of this. Suppose f of xy is equal to x squared plus 3xy plus y to the fourth. Partial f partial x, which in 280 we start abbreviating as just this. Take the derivative of this with respect to x and pretend y is just a constant. So 2x plus 3y. Partial f partial y is going to equal 0 plus 3x plus 4y cubed. And what we find later is that if you're in a simply connected region, in a simply connected in R2, and the simply connected means there's no holes in the region. You get this result that the mixed order partials, the order doesn't matter, meaning you can do y first and then x first or then y. Okay, and this is Clairaut's theorem. Okay, so why is f of xy equaling c the implicit solution? So remember, we're kind of implicitly assuming that y is a function of x, right? So the df thing would actually be the derivative of this whole thing, which would be this dy dx times the dx thing. Okay, well, anyways, I'm not trying to go through all of the details of this. Okay, so there's a test here for exactness, okay? So definitely, well, first of all, we'll define this, okay? Definition. If you're given this differential equation, m of xy dx plus n of xy dy equals 0, if there exists an f such that partial f partial x is equal to m, partial f partial y is equal to n, we say the above differential equation is exact. Okay. What you guys in 280 will be saying is that there exists a potential function. Okay, so here's how you decide if it's exact, okay? So if partial m partial y is equal to partial n partial x, then the differential equation is exact. Okay, so this is the test for exactness. Then m dx and dy equals 0 is exact. Okay, now the reason for this is this. Like, if partial f partial x is equal to m and partial f partial y is equal to n, then we must have, since partial squared f partial x partial y, which is partial m, because we haven't taken the derivative with respect to y yet, these two things are going to have to equal each other due to Clarue's theorem, as long as we're in a simply connected region. Partial y, partial x, my partials look really bad, and this is the partial n, partial x. So if these two things aren't equal to each other, the thing cannot be exact. Okay, because Clarue's theorem always holds. Now, if you're in a non-simply connected region, all bets are off and you have to rethink your problem. Okay, now these guys aren't really too terribly difficult. Okay, writing it out in general is actually more difficult. Okay, so let me do an example of this for you here. So, no, there's the cards there. I'm actually doing some shit. Let me find exact. I'm not in my normal book. Exact differential equations. And he's done. Find it now. Okay. All out. And this guy here. And okay, here we go. Let's see. Okay, so let's try this example. Where the hell did it go? Using it. Hold on a second. I gotta find where this stuff is in. Can't take me too long to come up with one on my own. There we go. Okay. Okay, so for example, let's look at this guy. I'm going to have y over x dx plus 1 plus the natural log of x times y dy equals 0. And in the problem, it's been given to us that this is 0. Okay, so the test for exactness. Okay, so I'm not, in 285, I do this in complete generality with the proof, just so a couple people can see it. I don't think you guys need to see it just yet. If you want to, you can stay after. I can dig it up and maybe take pictures of it and stuff. But anyway, so the m is this y over x. And the n is this 1 plus the natural log of xy. Okay, so we want to look at what the partial derivative of this is with respect to y. And what we see is it's 1 over x. And the partial derivative of n with respect to x is going to be 1 over xy times the derivative with respect to x on the inside, which is just a y. And so this thing is exact. Okay, so the procedure here is pretty straightforward. So there exists a function f such that the partial derivative of f with respect to x is y over x, and the partial derivative of f with respect to y is 1 plus the log of xy. By the way, the restriction that x is 0 now forces y to be, the restriction that x is positive means that the y must be positive too, if you can tell. Okay, so what we do is we kind of back into this. So if we were to integrate y over x with respect to x. So I had a junior teacher, my junior year at Cal Poly, we were doing this, and this is how Dick Robertson wrote it. You know, he said, okay, this is like partial integrate. So you just think of y as being a constant. Okay, so this is going to be y times the natural log of x plus a function entirely of y. Let me write that down better. Okay, so f of x, y is going to be the integral of the y over the x, but we're only partially integrating. So that's notation. Okay. So what this is, it's y times the natural log of x, don't need absolute value because x is positive, plus a function of y all by itself. Because if I took the partial derivative with respect to x of what I result with, this whole thing would disappear. Okay, so now what we do is we compute partial f, partial y, and we set it equal to the n, okay? So the derivative of this is the natural log of x plus h prime of y, and something is amiss here. That's supposed to be, where'd my y go missing? I'm making a boneheaded mistake here.
Y to the left.
So that's the expression we need to get.
Okay.
Okay, so where am I doing this wrong here? It is exact. So I integrate this with respect to x, and that's going to be y natural log x plus that. Take this derivative. Oh, because I'm being stupid. So, no, I did that right. Partial derivative with respect to y is going to be the natural log of x. Oh, I see what it is. Plus h prime of y. This has to be the n. Okay. Now the whole problem here is to find the h prime of y. Now notice that n has been sneakily written like this, but it's really this. From our logarithm rules. Okay, so these two things cancel out. And so just as advertised, we have something in just y. 1 plus the natural log of y. So that means that h of y is going to be this integral y plus y natural log y minus y, like so. That's the integral, right? The integral of log x is x log x minus x. Somebody check me on that. Okay, so our f then is this y natural log of x plus this h of y, which is y natural log of y. Okay, and the solution is this whole expression equal to a constant. So this is a hardcore implicit solution. Okay. Okay. So just to give you a little bit more of a justification of this, okay? So y f of x y equals c is the implicit solution. Okay, so we have our exact differential equation. And then it's going to be an m dx plus n dy equals 0. So he writes it as, we write it as a differential equation like we would normally see, equaling 0. And then what he recognizes is that m is the partial derivative of f with respect to x. Okay. And wait, this m's not supposed to be here. That's just the n right there. Okay. We divided everything by m dx. Okay. Now this n is partial f partial y, then this times dy dx equals 0. Okay. Well, notice that df is equal to this expression. It's the partial of f with respect to x times partial x. See, it kind of just goes away. And then partial f partial y. And then we are assuming that y implicitly is a function of f. And so that's the justification. These things cancel and give you 1. Okay, so these are actually very mechanical when we are doing these things. Okay, so try one more. And it's good integrating. So let's see here. Let's try this guy. Y squared minus 2x dx plus 2xy dy equals 0. Okay, so this is our m, that's our n, and my is 2y, and that's the same as nx, so it's exact. Okay, so I've got a function where the partial derivative of it with respect to x is going to give me y squared minus 2x. So that tells me that the f must be x y squared minus x squared plus a function entirely of y alone. So then I go partial f partial y, and that's going to be 2xy plus h prime of y, and that is going to equal the n, which is 2xy. So this says that h prime of x of y is equal to 0. So that means that the y is, the h is a constant. Okay, so let it equal 1. Let h of y equal 1. We'll have the arbitrary constant. So xy squared minus x squared equals a constant. Now this one you can solve for y with the plus and the minus. Okay. So what do you guys think? We've done the basic first order stuff. There's one other thing that we can talk about. And he could have very easily put these things in the textbook and not done all the storytelling. But that's with what are called homogeneous differential equations. So maybe on Monday, I'll start looking at those things with us. But I definitely want to get to second order so we can use our power series stuff. All right, so remember, we're not meeting tomorrow. We got family function going on. And I figure we could all use a break from taking a break, you know. you working, Eduardo?
Yeah. I've been working from home, and then that part-timer at that gas station. I babysit it.
Nice. Free gas?
I wish. I don't get much free. I think I only get like a free car wash a week,
Yeah.
which I only use it on my trucks and the SUV.
My truck, on all the car washes near me where your car goes on a track, my truck